Welcome all to today's Passive House Alberta Coffee Talk. My name's Frank Crawford. I'm the Education Committee Lead with Passive House Alberta, and today you'll be hearing from me about a grant or an extension of a grant and some work that Passive House Alberta is working on. And it is all around kind of electrification, peak loading, and kind of the impacts that high performance homes could have on the grid. So if you have any questions, put them in the chat box. If not, I will get started, but there will probably be some points during the conversation where I stop to kind of have a bit of a conversation. So why did we kind of looking at this peak load survey, the whys? And so we kind of started with that. Some of the naysayers, you can call them climate deniers, whatever you want to say that if we just kind of take the current electrical grid and we then take everything that is now on natural gas or everything else and we electrify all our buildings, that the grid is going to have to get kind of 2 to 3 times larger. This is like including all the generation, the transmission, the transformers, and everything down to the house. And obviously that is a fairly nearly impossible and very costly option to do. So we want to actually do some research to see if, when we electrify buildings, if this was actually a problem or is just kind of fear mongering, I guess you could call it. And we already know from lots of experience, Passive House has been around for 30 years, that high performance buildings and passive house buildings use less energy in their space heating over the entire year. That kind of 80 to 90% reduction in space heating is what we're used to seeing, and we are seeing happen in all climates, even cold Alberta climate. So high performance buildings use less energy. So if we are using high performance buildings, is the impact on the grid the same or less? And to some extent, kind of the electrical grid is going to have to be sized on the electrical service to each building, because when we say we get a 100 amp service or a larger service from the grid, we are telling the grid that we are going to use that much electricity at any given time. And so the grid has to be able to be sized to provide the electricity. And obviously there are some kind of coincidence factors that the grid managers will assume so that not all 100 amps times however many homes will be available. There's always some kind of factors that are involved. So kind of understanding what those factors need to be is also kind of some of the goals of doing this peak load survey. And it is kind of an extension, and we can also talk about the previous report that Passive House Alberta put out, which is called Electrification Without a Service Upgrade. And it was basically looking at, from a code calculation point of view, can we electrify all the different services in a building, change everything from gas or whatever it is, change it all over to electrification. And the results were kind of that, using some different types of load share devices and other watt diets and other things, that most of the time we could electrify a single family home on that 100 amp service. And that 100 service is what is most common in Alberta and many other places of the electrical service going to the building. So what about the worst case scenario? What happens when it's really cold? So fortunately, the worst case happened in January. So as probably most of you remember, it got pretty cold, got down to minus 46 in some places in the province. So that is our worst case scenario. It's actually beyond what we call the design temperature of Alberta. So we applied for some funding from NBIX, which is the Emissions Neutral Building Information Exchange, to do some research on what the impacts were. So the research is still ongoing. This is just a preliminary data. So far, we have about 30 residential homes that have submitted survey data, 1 commercial building, and 3 multi-unit residential buildings that we have data from. So it is a small sample size, but we're I guess, taking some leaps by saying that it is fairly informative of what a fully built out high performance buildings could look like. All buildings that were in the survey currently were some type of high performance construction. So if there are people on the call that live in kind of a more of a code minimum building that would still like to participate in the survey is still open. And ideally, to participate in the survey, you do need some form of energy monitoring system. However, if you live in Edmonton and you want to participate in the survey, you could send myself an email at frank.crawford@passivehousealberta.com, and I can send you a little form, and then EPCOR, which is the utility provider in Edmonton, will provide me hourly data for any of those buildings. Because with these 30 homes, we kind of know what high performance homes are going to perform at, but what we need for the comparison is what kind of code minimal homes perform at. And some of the homes, some are new builds, some are what's called deep energy retrofits. So again, a good combination of new and existing. So as we start to get into some of the results, I think I should spend a few minutes, because even I got confused because I'm not an electrical expert, on kilowatts versus kilowatt hours. So kilowatts or watts is a measure of power. And in this case, it's the measure of the electrical load at any given moment. So you can think about that as the rate of water coming out of a pipe. And then kilowatt hours or watt hours, that's a measure of energy or the electrical consumption over a period of time. So that water pipe in kilowatts is dumping into the bucket, and how much water is in that bucket is kilowatt hours. And then kilowatt hours are what we see on our utility bill. That's over a period of time. But at any given second, our building will be using a certain amount of kilowatts. So kilowatts applied over time gives us kilowatt hours. So how big were, kind of the first question, how big was the electrical services to each of the units in the survey? And we can see here that very few of them, actually only about 25% of the homes stayed on that 100 amp service. The majority of them upgraded to either a 200 amp service or even some larger, but not many of them stayed on that 100 amp service. And so the next question was that a problem? Could they have stayed on a 100 amp service? Because we want to stay on a 100 amp service because that's what the grid is already kind of used to providing. And if we can maintain that, then the impact to the grid is going to be reduced. So this graph just shows the red line is a 100 amp service, each one of our kind of 30 or 27 homes, and what their electrical service to the building was. Okay, so did they need a larger one on that coldest day of the year when it got down to -46 Celsius in some locations? The answer is generally no. So the red line there on this graph is 24 kilowatts. And that is the theoretical instantaneous 100 amps times 240 volts that could be kilowatts that could be flowing from the grid into the house. Now, if it went for too long of a time, there would be a reduction by 80% of that, but we're taking 24 as a theoretical. So as you can see, only one peak 15 minutes. So this is how much kilowatts were flowing over 15 minutes. So it's not kilowatt hours, but it's kilowatts for a 15-minute average. There could be shorter instantaneous averages that are larger, but generally we broke it down to 15 minutes because that's generally what the energy monitors will spit out, and that's a long enough time that it starts to make a difference. So only one house went over that 24 kilowatt line, peak line, and it included in the 25 kilowatts, it included 8 kilowatts of electric vehicle charging. So if we break out electrical vehicle charging from that, because we can control electrical vehicle when it charges using what's called a circuit pauser load share device. If we break that out, then the vast majority of the buildings were in kind of a 10 to 15 kilowatt, 15-minute peak load range. And that is much less than the theoretical 24 kilowatts. As interesting, there was a passive house, had one of the lowest peaks. It was 4.8 kilowatts. So it only took 4.8 kilowatts of electricity flowing to keep this all electric passive house warm on the coldest days of the year. So this is, again, preliminary data, but very encouraging that we probably don't need to upgrade above that 100 amp electrical service. So the next question, and this one I don't have an answer for, this is what we're still kind of looking for, those comparables to compare about, is that 10 to 15 kilowatts, is that too much for the grid? It is only 40 to 60% of what is allowable on a 100 amp service. But, and as I said, the utilities always factors that that not everyone's going to be using that full 100 amps at the same time. So if all of us are using 10 to 15 kilowatts, then the grid might have to get somewhat larger. But so I'm reaching out to some utilities. If there's any on the call today, definitely connect with me to see, kind of get some of these answers on how big of a problem this is. And it might be a generation problem, like we can't actually produce that much electricity, or it might be a transmission problem that we can't distribute that electricity to all the individual houses. Might be both. So I guess, so as a question, with my house, so my house was in the study. I live in a passive house. It is a duplex. So my peak was in that kind of 10 kilowatt hours with a duplex. So another question that seems to come up all the time is, do heat pumps work in our cold climate? And the short answer is yes. At minus 46, the air source heat pumps won't actually be producing any they won't producing much heat from the air. So much below minus 25, minus 30 with some equipment, all air source heat pumps will be using what is called the secondary heating system. So their compressors will turn off and they'll go to the secondary heating system. That can be an electric heating system. It could be a fossil fuel heating system. And historically, there's only about, I think, 5 days in Edmonton that are below minus 25, and only about 4 days in Calgary over a year that's below minus 25. So we will need a secondary heating system if we're using an air source heat pump, but it won't be used all that often. And the rest of the time, air source heat pumps work fine. Even at minus 25, I have an air source heat pump in my house. It was had no problem keeping up, providing all the heating for my house at still a fairly good coefficient of performance. So basically it was using less than 100%, or it was producing more than 100% electricity. So it's better than electric resistance. In other words, for say 1 watt of energy in the compressor, it was producing probably 1.5, maybe 2 watts of heat. And air source heat pump technology is always getting better. So we might be able to kind of get lower than that minus 30 threshold. And interestingly enough, the Tosot brand, which is a type of green manufactured product, their cold climate air source heat pumps were used in some passive house certified multi-unit residential buildings in Edmonton, and they worked without any secondary heating system. So if we get the envelope higher enough performance, the buildings are small enough, then these air source heat pumps can work without any secondary heating system, is what we're finding. And if you're interested, the next month's Passive House Coffee Talk actually is with Tosot, both the kind of VP of sales for North America, as well as the Passive House developer will be on to talk about how the Tosot brands worked. But they are seeming to have very good functionality. The other option is you could use what's called a ground source heat pump. Instead of using the air, they use the ground as their source of heat, and they do not care what the outdoor temperature is. So there was 3 or 4 ground source heat pump heated homes in the survey, and they worked no problem, continuing about a COP of 3 to 4. So 1 watt of electricity for the compressor made 3 to 4 watts of heat into the building. And their peaks were, for the compressor, kind of 2 to 5 kilowatts. There's a question about this graph, and yes, it was all of the energy use for the building, so incorporating everything: space heating, electrical loads, plug loads, everything. So now we're also, as part of looking at just the electrical grid impacts, we did, as part of the survey, do some comfort and other questions. So we asked about window condensation, because kind of choosing your windows will definitely have an impact on how much condensation you're going to get on those windows. So some of the buildings had Passive House certified windows. Some of them just had high performance triple pane windows. I don't believe there was one or two actually that had even double pane windows. So as you can see, there was a fair amount of yeses as far as was there window condensation. There's a few no's. There's a lot of a littles. So basically what we could kind of see is as the windows got higher performance, because we did actually ask in the survey about the window performance, the specs. So as the windows got higher performance, the condensation impact was less, which makes sense. Higher performing windows are going to have a warmer surface temperature. Warmer surface temperatures are going to have less condensation on them. However, at minus 46, there is likely going to be some condensation. In my house, I have cool climate certified windows. When I dropped the blinds, because I was stopping the heat from getting to the window, when I raised the blinds in the morning, there was some condensation. So even if you buy the highest performing windows, you are likely to see some condensation. The other answer why there is a number of no's for this condensation is if you have a existing building or a deep energy retrofit where they have a heat source that is always blowing warm air over the window, that's how lower performing windows, or how we're currently with code minimum, how we're getting around that condensation problem with windows is if we put an additional heat source that blows warm air over the windows, it takes the condensation away. But if we have high enough performing windows, then we don't need that heat source at each one of the windows. So that's why there is 40% of the no window condensation, because they have a heat source blowing that warm air, because at minus 40, that furnace is going to be running probably constantly, is blowing air over the windows. The other questions were around comfort. So we did ask, was there any kind of comfort concerns that any of the occupants experienced? And I guess on the good side, there wasn't any. So even down to minus 46 in the high performance homes with the heating running, there were no comfort concerns. So that's good to see that building science applies, thermodynamics applies. If we make sure we are building high performance homes, we're going to be comfortable. Some of the homes that had done less building envelope upgrades weren't any more comfortable after electrification, but there was never any drop in comfort from electrification. So we said it before, we'll say it again, a high performance envelope is what delivers comfort. Your mechanical system can kind of try to replicate that comfort by providing lots of warm air all around the building, but it's the envelope that actually provides the comfort. So I guess that maybe a bit of a question to the group is kind of when it was, for those of us living in Alberta, that hit minus 30 or minus 40, that cold temperature, how were your houses? Did you have to run a few electric heaters in addition to your furnace? You could just maybe put answers in the chat box if you want. But yeah, so I'm just kind of wondering how you people in the cold temperatures, what happened? Was it cold? Did you have lots of condensation? Did you have icing on your windows? Did you have to run those extra heaters, or did kind of your code minimum house keep up? Yeah, so I think we might be already talking to mostly the converted. So a lot of us live in the high performance houses, but yeah, so I guess kind of keep your eyes open if you know people that live in code minimum houses that want to kind of participate in the survey. That would be great to get some more information from them. So the other kind of part of this whole peak load survey is kind of talking about that grid emergency that I think we all experienced when the grid was almost not able to provide the electricity, and kind of the add-on of resiliency. So resiliency can be kind of defined a number of different ways. The way I like it is basically how well a building or a system can kind of deal with changes in its environment or to its external forces without having a detrimental effect. So if we take this to buildings, how well can our buildings cope with extreme heat, extreme cold, grid outages, all these other things, high winds, flooding that might occur without actually compromising the ability of the building to keep you safe. Because remembering our houses, their primary goal is to provide shelter, keep us safe from the elements. So here are a few kind of some quotes that came out from the survey. So this was I think from a passive house. So when the grid emergency was called, they turned down the heat and all extra lights and unused appliances. There's no concerns as the house kept the temperature well. The peak dropped considerably as there was minimal usage. So as we live in more high performance homes, we are able to, for short or even medium periods of time, turn off most of the heat to that building. And it's very resilient in that it won't actually change temperature that quickly. So here's another example. I unplugged one 15-watt electric heater and turned all the thermostats down 2 degrees. The sun had warmed the house up to 23 degrees during the day. When it got up the next morning, the house was only down to 19.5. So another kind of key feature of passive house is that we're trying to use as long as we can see the sun, and Calgary and Alberta is a very sunny space. So as long as we can see the sun, have that good solar availability, we try to use that sun's free energy to heat the building in the winter and then through the windows, and then we're shading those windows in the summer so we don't overheat. So even when it was -30, -40 outside, if the sun is out, we can still heat our building with that sun. Obviously, when the sun goes down, the building will start to drop. But in this example, it really only dropped kind of 3.5 degrees over a whole night, turning the temperature down 2 degrees. So it's really stayed at its set temperature. You drop that temperature down and the building slowly dropped. So I think these last two quotes are from passive houses. So really showing what a passive house building envelope can do. So the first one, this was a passive house. It wasn't even fully built. It was under construction, but the envelope was kind of 95% complete. So there was no mechanicals operating. There was no one living in it. There was no internal heat gains. So they're heating the house with a single 4,800 watt electric resistance heater, which is actually less than the heating design load, which I think is about 5.5 kilowatts for this house. And that heater was able to maintain the temperature overnight. And then when the sun rose, the interior temperature rose as well. The house basically just didn't care what the weather was outside. It was able to kind of keep along, maintain its temperature with a very small electric resistance heater in it. And there's another passive house duplex where all the heaters were actually turned off when that grid emergency was called. So a full 2 families house, I think 4 people living in it, turned off all the heat overnight. And when they woke up the next morning, the house had only dropped 2 degrees. So that's what resiliency should look like. So if the grid did go down, they would also be fine. They would drop their peak demand from, I believe, about 5 or 6 kilowatts down to 1 kilowatt overnight by turning all of the heaters off. Again, there's still a lot of what we call phantom loads in the background that still kind of add up, but there was no specific heat to this house, and they only dropped 2 degrees over a whole night at, I think, -35. This was in Calgary. So for those that think a furnace is a more resilient option, it can be, but remember, as your furnace will not work without electricity. The furnace needs electricity to run the blower, the fan that moves the air, and all the electronics of a furnace. So unless you have like a really old, I think like gravity-fed furnace, you need electricity to run it. However, if you live, talking again about resiliency, if you live in kind of a rural location, and I think we'll have a bit of a conversation about this because I'm almost done my slides, so we got lots of time for conversation. So if you live in a rural location and the potential or the frequency of grid outages or brownouts or rolling blackouts, whatever you want to call them, is higher, and you already have a propane tank on your property, if you do a deep energy retrofit or if you build a new high performance home, keeping that propane tank as your secondary heating system to your cold climate air source heat pump as a primary is probably a very resilient strategy. If you then added on either a small generator or an EV and in a few years, hopefully we'll be able to vehicle to grid or vehicle to house charging, that propane tank and your small EV, you could basically go off grid probably for a week or two and not have any problem. I actually calculated how much energy my house needed over the week and then converted it to kind of propane tanks. And if I had I think 6 kind of 20-pound, basically your barbecue propane tanks or 200-pound propane tanks, that would do all of the heating of my house for about a week. So propane, I think, is still a fairly resilient option, and it gets you off of all those fixed connection fees with your natural gas connection. Because leaving, if you're only going to use 4 or 5 or maybe 10 gigajoules of energy, natural gas over the whole year, paying that $450 to $650 fixed connection fee for natural gas is probably a pretty high number. So some of the initial conclusions that we've drawn is that it looks like there is no either code calculated reason or actual peak 15-minute or 1 hour consumption or load reason that we need to go over that 100 amp electrical service. So try our best to try to stay on the 100 amps. We are then giving signals to the grid that you don't need to get that much bigger. It still needs to be efficiency first. So start with a good envelope. That will reduce the need for heat, however we meet that. Ground source heat pumps have little to no peak load impact. They just kind of keep humming along at that kind of 2 to 5 kilowatt range. And fossil fuels as a secondary heat system will lower the peak electrical grid impacts. So it's good for the grid, but has higher greenhouse gas emissions. So kind of deciding our secondary fuel source is still kind of definitely up for debate. And if we're trying to meet that goal of being net zero energy or no greenhouse gas emissions or no longer using natural gas at all by 2050, we are likely still have one mechanical system replacement before then, because furnaces as they become more complex, they're probably not going to last much more than 20 or 30 years. So if you want to do an upgrade now, put in that hybrid system, which has an air source heat pump and a fossil fuel furnace, that's probably fine. And then just kind of design it so that as you do your envelope upgrade, you use less and less gas, and eventually you can turn off the gas, and then that air source heat pump will provide all of the heating and cooling that you need, and the kind of blower fan from the furnace will still move that air around your house. So really that is the end of the slides. So now we got lots of time to kind of have the conversations, have whether or not we want to go to kind of electrification or stay on the peak loads. There's a few pre-asked presenting questions that I'll bring up if no one else has any questions, but definitely if you have any comments, feel free to kind of unmute and yeah, have a bit more of a conversation.
Yeah, I've got one here, Frank. I just wanted some clarification on the what the houses, the characteristics of the sample sizes were. Like, were they all passive house, single family homes, townhomes, or just higher performing in general?
There was only about, let's say, 4 passive houses. The rest were all higher performing. So we did ask for, if they have it, an enter guide label, and if not, just kind of the performance specs of the walls, the floors, the roofs, and the windows, and the ACH of each of the buildings. So we have a pretty good idea of the performance of all of the buildings. So I haven't done any real big analysis trying to draw out like design heat load versus peak load or anything else like that. But yeah, they're all some form of high performance, varying degrees, varying sizes.
Gotcha. And then that's why you're asking for the code minimum kind of input now.
Yeah,
That's interesting.
that's really the big question is that 10 to 15 kilowatts, is it twice what a code minimum building does? Is it the same? Because like anecdotally, I've heard of a lot of people, they might have had their furnace running and maybe had 1 or 2 electric resistance heaters that they needed in addition to their furnace to keep their building comfortable. So if they're doing that, when you add up all the other things, they might be a peak load of 5. I think we have 2 buildings that are using a furnace in addition to an air source heat pump, but a furnace is a secondary, and I think their peak loads are in the 3 to 5 kilowatt range. So yeah, again, we're still more data is good, but we're getting to some conclusions.
Just a quick question.
Yep.
Is anyone looking at small natural gas cogen like Ingenuity or companies like that as far as supplying multifamily units where you'd have one cogen unit for multiple passive house builds?
Yep. Yeah, there's a number. I think both SSRIA and Emissions Reduction Alberta are funding a number of cogen studies. And I like how you added on for multifamilies. I think cogen probably for a single family is probably overkill, or you don't have enough load for heat to justify it. But once you go to multifamilies, that's when, like, yeah, the ground source or cogen starts to become more advantageous because you have more demands. And cogen is just basically when you are producing hot water, you are also using some of that heat and steam to create electricity. So you get both from the same thing. So yes, I think there is still a use for that. And yes, there are, I think SSRA and other has some examples of it. There's a question about PV and the 100 amp service. So if you read the electrification without a service upgrade report, it shows you how to get around that kind of bus bar issue of, I want a big solar PV array. Do I need to upgrade my service? And the answer is no. You might need to upgrade your panel because what the PV system is looking for is a larger bus bar. The bus bar is basically the wires behind or the wires within the panel that distribute electricity. So you might have to put a 200 amp panel because the bus bar sets the panel. So you put a 200 amp panel, which gives you lots of space to connect your solar into the bottom, but then you still only put that 100 amp breaker because that's what sets your service size to the grid. The other option you can use is what's called splitters. Splitters basically from the meter base, where the meter, or electrical meter, splits electricity. One goes to the PV system, one goes to your panel, and that's the other way to get a large PV system on while still maintaining that 100 amp service. Other questions? I think there was another question that was along the lines of that. Just talking about some of the smart electrical meters. So again, talk about them more in the report, but I can have a brief conversation about them now. So the smart electrical meters or smart circuit breakers, which are starting to come up, well, they work similar to a load share device in that they control the peak amount of electricity that flows through it. So there's called the Coben Genius, and that is a smart electrical panel, replaces your whole electrical panel and gives you 24 circuits that you can control, monitor, and prioritize to make sure you never go over that, say, above 100 amp service. The Coben Genius, I think, would be best suited for, again, a multifamily because it can have up to 400 amps of load. So if you have four units, all going back to one Coben Genius, you could still probably have a service connection from the grid at maybe 200, 150 amps, and you just load share everything within it. There's also the SPAN smart electrical panel. It's currently only available in the States. I have heard that it might be coming to Canada, but I don't know. Again, it works very similar to the Coben Genius in that each circuit is controllable. Then there's also the Lumen smart panel. It's a smaller smart panel that just controls up to 6 circuits. So it's an add-on to your electrical panel. And then there's also the Lumen, sorry, I just need to find it. One sec. Lumen, I believe, Edge, or it's what looks to be, and again, I just did some research this morning because the question got put in beforehand. Not sure if it's available in Canada, but it looks to be kind of a way to put a energy monitor on each individual circuit as an afterthought. You just basically put it in line with the electrical wiring, and then it acts like a smart control panel. The concern that I'm not sure about the answer with for those is they all have to be connected to the internet. So what happens if the internet goes down, or if the power outage goes down? What do the kind of the smart controls default to? Because if you're relying on them to not go over your peak, if the internet goes down and you lose all those controls, but you still have electricity, could you go over that 100 amp service and start blowing breakers, which isn't ideal. And then the other one that again looks promising, Leviton, which is one of the larger electrical equipment providers, now has their smart circuit breakers and load center. So you can basically put in an electrical panel, and then you can put in individual circuit breakers into each one of those controls, and then you can control that smart circuit breaker with an online app. Again, my unknown question is, if the internet goes down, how does that app default? All right, any other questions or hands up? Feel free to just unmute.
Just about smart meters again. I'm not too sure if I just heard somewhere that some jurisdictions don't like accept smart panels as part of like a justification for having a smaller amp size. Like if you go over your amp size and you have a smart panel, I've heard that some jurisdictions don't allow that it's not an acceptable solution for them.
Well, so I think with that question, it would come back to that kind of, is it hardwired? What I've heard now is, as long as the electrical appliance is hardwired and has those built-in hardwired controls so that you won't go over the set peak, then it's okay. The ones that I'm not sure are maybe these Leviton ones and these other ones that use some type of internet-enabled controls, and what happens if the internet goes down. So we in a previous grant, we did install the Coben Genius. There's been a few installed. They've been around in Canada for, I think, 15 years. So I've never heard them not being able to install the Coben Genius. The span isn't certified in North America or in Canada yet. So it is making sure you have the right ULC certifications and that hardwired, or what happens if the internet goes out.
Okay, thanks.
Frank, Shane had a couple questions. I know that you may have almost addressed all of this, but just to say, what about the CSA regulations in terms of size of panels or service?
So as far as I understand, for all the CSA, when you're sizing your electrical panel, there is a number of code clauses that you run through all of your electrical appliances on, and you add them all up, and then as whatever number you get, that is the service size that you need. And then if it's over 100 amps, then that's when you start using those load share devices to make sure from the calculation point of view, you're able to stay under those 100 amps. But we haven't. So I haven't hit a building yet that we haven't been able to keep under 100 amps, unless we start going to secondary suites and like a second large range, because the ranges are a pretty big 40 amp, 240 volt circuit. So if you have two of those, it gets tougher to stay on 100 amp service. But for single family homes, I haven't had one yet that we can't keep on 100 amps, but you might need to use one or two load share devices and smart appliance selection. And I believe also, like within the code, there are people reviewing that there's a kind of a set watts per square foot that the code includes. And I believe in the next iteration of the electrical code, they are reviewing that, because as we have moved away from incandescent lights to LED lights, that kind of baseline watts per square foot or watts per meter squared is dropping. And that's kind of also what this peak load is showing, that if we did from the calculations, we should be much higher than the 10 to 15 kilowatts peak. But what we're seeing is the actual peak is less, because not often everything is on at once. And we found that for kind of lower performance homes, the peak was more closely related to the heating design load, meaning that it happens at night when the building is being heated. As we get closer to the passive house and high performance or higher performance passive house buildings, the peak 15 minutes is actually more likely to occur when cooking or washing or something else. Because if our peak heating design load is only 5 kilowatts, if we turn on our oven, that's kind of 2 or 3 kilowatts. If we happen to have a toaster or something else on at the same time, if it's on for 15 minutes, like we're running an oven or a toaster oven, our peak for high perform or passive houses are more likely to be during cooking, those kind of 5 to 6 p.m. peaks. So when it occurs will also depend kind of on the higher performance. So I guess another extension that we're kind of starting to look at, and maybe that'll just be one of the next grants or the next pilot projects, is looking at district energy. Because obviously if we move the space heating, which is still going to be the largest amount of energy that we need for a house, even in high performance, if we move that space heating energy from on-site production to some off-site production from the district energy system, we can then have lots of options on how we produce that energy to lower the grid impacts. And then we're just basically distributing hot or cooled water or fluid to each one of the houses. And then you can meter them with just a flow meter.
I wonder, because Frank is still working on this report, if anyone that's on the line today has any ideas of what they'd like to see in conclusion from the survey and from the report. If there's anything specifically that you'd like to see addressed.
Yeah, I guess, or what are some of the challenges that those that are trying to do the deep energy retrofits or build the high performance homes or just stay at 100 amps? What are those challenges that we're still seeing out there? And then how can hopefully these reports help kind of solve some of those challenges? Everyone's so quiet. I was expecting much more like comments or pushback or discussion. But that's okay.
Pushback, yeah, especially pushback. Yeah.
I'll break the silence. But no, I think what you've talked about like justifying 100 amp service, I think seems to be always the question that comes up. Just from my end, I run some deep energy retrofit fully electric projects here in British Columbia, and that's oftentimes like the first question that comes up is about keeping service, or do we need to like what is there going to be some sort of like cost, like unsurmountable cost in terms of like trying to upgrade the electrical service for these homes. So I think that would be great, and I just thank Ben and the Saint guys for inviting us to this call as well.
Yeah. So the electrification without a service upgrade report is out there, and that covers kind of most of the code calculation clauses on a way to get around it. Because yes, right now kind of the default is you do a deep energy retrofit, you go to a 200 amp service, and we want to try to kind of change that, because if enough of the people start doing those 200 amps upgrades, then eventually the transformers locally in your alleys and then going all the way back up the system is going to have to get bigger. And that's when those fixed transmission fees start to grow up, because the utilities get to charge us as the consumers if they have to upgrade the grid. So again, we're still definitely at the distribution of the information as far and wide as we can get. And yeah, trying to now pair it with some actual data in addition to the code calculations. All right, looking through the questions. Was there another question? So there was a question about smart metering or time of day pricing. And actually, I think this came up a bit in the Alberta Energy Efficiency Innovation Summit that was here last week in Calgary. It'll probably still be a while until we get time of use billing in Alberta, just because to do that, all of the meters, depending, EPCOR is a little bit further ahead on meters, but Calgary and most of the other, and Fortis, I believe, would have to upgrade all their meters before we can do that time of use or time of day billing. So we're probably just staying on the current electricity rates and being able to switch between our high and low kind of solar club rates, which we have in Alberta, which is beneficial for on-site renewable generation. So it might come, but it'll probably be a while before we get it in Alberta. All right, that's most of the pre-sent-in questions that I had. So we still have a few more minutes left. If there is any other questions, I guess we can open up to more broad energy efficiency questions around electrification. They all seem to kind of combines with each other one. And if not, we will see you next month. Right, if there's any questions, I will end the recording, but I'll stick around for a few minutes if anyone else has anything else to bring up.
Maybe I'll throw one more in, Frank.
Okay.
I did actually have you as my passive house instructor for one of my courses a few years ago now. But do you see battery storage playing a part, like on a residential level in the work that you're doing?
I think where we're going to get battery storage is going to be from the EVs, because the battery in the EV is so much bigger and more cost effective than just a standalone battery. And until we get that time of use billing where you can really optimize when you're buying and selling electricity, the cost effectiveness of a dedicated battery varies. Like in California, they're definitely doing it. There's virtual power plants that are being installed using batteries because they have that time of use billing, and they can decide when they're buying cheap electricity and then we're selling expensive electricity. But in Alberta, till we get that time of use, there is the financial incentive to pay that $10,000 to $15,000 for that stationary battery just isn't quite there. But an EV, once we get vehicle to grid, which I think we're just waiting for the certification in Canada because it exists in the US. Once that comes in, then using your car battery, because most people, unless you're driving a whole really long distance, might only need half of that battery daily. So if you use that other half of the battery to reduce your electrical consumption, or demand response, where a utility could send out a request for additional power, and that's called a virtual power plant, using all these EVs all around the province is actually a fairly easy way to add grid storage. I think, again, California is kind of leading the charge with those options. So might be a while in Alberta, but other places that have time of use billing, it's already occurring.
Yeah, nice. That's what I've found as well too. The time of use rate is definitely the trigger point for that distributed resource.
Yep. But it's coming. Like, it's the kind of demand response, or being able to have utilities control some of our appliances and compensate us for that, to help reduce that peak is something that people are looking at, because it's generally much more cost effective to do that than to make the grid bigger. If we can just reduce demand and the current grid can maintain that, that's kind of the most cost effective way to do that.
Mm-hmm.
Alrighty, well, I will end the recording and hang around for a few more minutes.